Okay. Hello, everyone. My name is Carl St. Louis. I'm an assistant professor of organic chemistry at Kennesaw State University. I first joined CCAS this summer. I think it was in July. So I'm the newest member. Me and McCarthy is the newest member here. So today, I'll be presenting some of the project that we are working on in my research lab. So I will first focus on this project on the design and development of pro-fluorescent o-Nitrobenzyl photocages for hydroxamic acid synthesis. And before I go any further, I would like to give a big thanks to the CCAS for inviting me to this talk today, and also for everybody online for coming to listening to us. So imagine walking into your lab to conduct an experiment, and no matter how hard you try, you end up with your final product in very low yield with multiple side products, and that actually make your purification very difficult, and there's nothing you can do about it, right? So as an organic chemist, I can tell you that I've experienced something like this, well, a lot, right? And it is very frustrating. So today, I hope I will show you what my research group is doing to solve this problem. So we are developing photolith-bioprotecting groups, or you can call them photocages, that absorb near the visible region of the electromagnetic spectrum. We designed them so you can photoplay synthetically hard to synthesize compound, or synthetically hard to synthesize biologically active compound with a self-reporting fluorescent byproduct that we can use to quantify the formation of products. So we are taking this approach because we wanted to bypass the harsh condition that scientists use in this reaction, for example, strong base and strong acid, strong oxidant. Instead, we wanted to use light to synthesize these compounds. So by using this, we're hoping that we can increase the yield of the products. So the first hard to synthesize compound that we wanted to investigate, it is hydroxamic acid. So the hydroxamic acid functional group contains a carbonyl group that is directly connected to an hydroxylamine group, as you can see here. Hydroxamic acid, they are widely used, for example, in polymer design, in analytical chemistry, and also in organic synthesis as a precursor to make isocyanates here for coating purposes. And also, the hydroxamic acid are used in the medical field for the building blocks of anti-cancer agents. So you can see that they are very important. However, the synthesis of hydroxamic acid, it is known to be problematic, right? So if we take a look at the classical synthetic routes that chemists have been using, for example, if you look at A, it relies on the use of a toxic reagent, potassium cyanide, and at the end, you end up with a low yield anyway, about 14% yield. Another classical routes that chemists have used to synthesize hydroxamic acid involve the use of very reactive acyl chlorides reacted with hydroxylamine. So you have competitive pathway. As a result, you have the formation of polysubstituted side product, which also reduce your yield very low. And another pathway, another classical route that chemists use, it is the use of strong bases and strong acid, which also result in low yield. So what we are doing in my lab, we are focusing on designing photocages with a core that can absorb near the visible region of the electromagnetic spectrum. And in the future, we want to go to the visible. And also, we wanted to produce a self-reporting fluorescent byproduct. So for doing this, we have taken three approaches. So the first approach, we wanted to create a core that has a coplanar geometry. So as you can see here, they have an extended conjugated pi system. And secondly, we wanted to incorporate a push-pull system into the core. So by incorporating a strong electron withdrawing group to one side, like a nitro group, and also a good electron donating heterocycle, like a thiophene. So that will create a push-pull system. So we're hoping by doing this, we can redshift the absorption and the emission, specifically the absorbance, because we wanted to go in the visible region. And also, we wanted to incorporate rigidity into the core. So for doing this, we have incorporated an alkyne linker. You can see in pink here. So this alkyne linker, it makes the core rigid to ensure that we have strong overlapping of the p orbitals. So also we can be able to redshift the absorption and the emission. So after designing this core, we synthesize these hydroxylamine derivatives here with the core. So this hydroxylamine derivative, it is extremely important, right? So with this hydroxylamine derivative, you can couple with any carboxylic acid derivative, and you can make endless hydroxamic acid onto these photocages. So here I'm only showing two cages, which is NPET PPG1 and NPET PPG2. Today, I'm only going to talk about NPET PPG2. So what we're doing, we are for us to start the photolysis process, to investigate the photolysis process, we're going to take those photocages and we're going to irradiate them so we can, number one, cleave the product that is hard to synthesize, which is hydroxamic acid in high yield. And also we wanted to have a self-reporting fluorescent natural ketone byproduct. So we first examine this the photolysis process by UV spectroscopy. So the absorption band that you see at 345 nanometers correspond to the uncleaved photocage. After irradiating for about 5 seconds, you see a new band that's at 395 nanometers. So this band corresponds to the acid nitro intermediate. So it turns out we were the first group to actually observe this band because it is so short-lived. And after irradiating for a couple of for 8 minutes, you notice that there's a decrease in the band of 295 nanometers with a new band appearing at 310 nanometers, corresponding to the natural ketone byproduct. Computational studies suggest that our photolysis mechanism for our photocage follows the o-Nitrobenzyl deprotection, which has been studied extensively since the 1960s and was first developed by John Baltrow. So basically, once you irradiated our photocage, you go from a ground state to an excited state, which is intermediate A. And the nitro group from the intermediate A abstract a hydrogen intramolecularly to form intermediate B, which is the AC nitro intermediate, which undergo irreversible cyclization to form intermediate C, which then you have ring opening to form the nitroso hemiacetal intermediate D. So from this hemiacetal, then you can cleave hydroxamic acid in high yield, and also you have your diagnostic fluorescent byproduct. So we wanted to see if we can see the fluorescent byproduct. So we investigate the photolysis via emission spectroscopy. So the weak emissive band around 443 nanometers correspond to the uncleaved photocage, and after 5 seconds of radiation, we see a new band appearing, which is the AC nitro intermediate. And after further irradiation for 8 minutes, we noticed that there's a threefold increase in intensity, which corresponds to the natural ketone byproduct. So if you take a look at this, the picture to the right of the graph, the cuvette to the left, it is before irradiation. And the picture to the right, you can see that it is emitting green light. So this is after irradiation. So that tells us that we have the self-reporting fluorescent byproduct. We also investigated this photolysis process via photon NMR. So due to time, I'm only going to focus on, I'm not going to talk about the peaks from the hydroxamic acid. I'm only going to focus on the peaks from the nitrous ketone byproduct. And I'm going to focus on proton H8, H7, which is here, and also H8. So if we take a look at figure A and the purple line, so this is H7. So H7, it is a benzylic proton, and it is coupling to H8, which has 3 protons, right? So you can see it is a methyl group, so that means H7 should be a quartet, and as you see here. And after irradiating, after 8 minutes, notice that H7 disappears, which makes sense, right? Because now we formed the carbonyl group, so this is the sp2 hybridized carbon, so H7 is not there any longer. So now let's take a look at H8. So we move to figure B and in orange. So H8, before irradiation, H8, it is a doublet around 1.6 ppm. And after irradiation, we see a singlet. This makes sense also because now, because H7 is no longer available, And also, you notice that the deshielded H8 is now deshielded, and this is due to the magnetic anisotropy of the carbonyl group on H8. So this makes sense. We also, which I didn't show here, so we also used a proton NMR to have how much hydroxamic acid was released, and it was about 95%. So already we have increased the hydroxamic acid release from 10 to 14% to 95%, with only one extra byproduct, which is the fluorescent byproduct. We also use FTIR so we can confirm the presence of key functional group. For example, at the end, we have a nitrosyl group, so we have to make sure that we see the band there, and also we have a new ketone that is formed. So, and also the hydroxylamine to make sure that we have all the functional groups there. So previously I showed you the absorption of our photocage. So it is absorbing near visible region of the electromagnetic spectrum, and however, you see there's a tail that absorbs around 425 nanometer. So we wanted to examine to see if we leave this photocage and ambient temperature and ambient light, and what is the half-life? I mean the shelf life of it, right? So we conducted this experiment. So we took our photocage, we put in an NMR tube, and we left it in a lab, and we just take NMRs every single day. And as you can see, after 30 days of leaving the sample at ambient room temperature and ambient lighting, we had minor degradation. And even after 30 days, all the proton signals remain clearly identifiable, tell us that this compound, it is robust, we don't have we only have minor degradation. So after conducting all this experiment, we decided, okay, we want to submit this for publication. So last month, we submit this to this project was actually accepted for publication in the Journal of Organic and Biomolecular Chemistry, and it was selected to appear on the cover of October, which is this month. So this was published last Monday, the cover. So we thank Organic and Biomolecular Chemistry for selecting our project. Okay, so in conclusion, I've showed you that we have developed a route to synthesize hydroxamic acid by removing the harsh reaction condition that chemists usually use. Instead, we are using light, and we did this by designing a photocage core that absorbs near the visible region of the electromagnetic spectrum, and also can release a self-reporting fluorescent byproduct. And we are able to synthesize 2 photocages, and we are able to improve the overall yield of hydroxamic acid from 14% to over 95%. And another project that we are focusing on in our lab involved the synthesis and investigation of fluorescent organic materials containing 3-coordinated boron attached to a nitrogen, carbon, and hydroxyl group, with the aiming of making multifunctional stimuli responsive material, as you can see here. So we're using one core, and we just trying to incorporate as much optical properties into this core. So the first paper from this project was published in 2023 in the Journal of Material Chemistry C, and we just submitted the second one last Monday, and it's under revision. We are also collaborating with the DCN member. I think Rochelle is very popular because I think Santiago also is collaborating with Rochelle. So Rochelle has experience in using benzoic acid derivative for latent fingerprint development. So in our lab, we're collaborating with Rochelle. We're giving her some of our compounds, which is the 3-coordinated boron compounds, and we are leveraging the high quantum yields of our compounds and also have the stability of them, right? And as you can see to the left, with the previous one that she published with the benzoic acid, you can barely see that you have fingerprints there, right? But if you move to the right, this is our compound that we gave her, and she's very fast. So we gave her this compound last month, and all of a sudden she's in this picture. She said, "Hey, we have something going on here." So you can clearly see that we have fingerprints, and I think this is a project that's gonna work out. Last but not least, I would like to give big thanks to all the people that actually did this work. I just kind of like manage them, right? So this is my graduate student and my undergraduate student. my postdoctoral associate, and also all my collaborators. So Samuel from Georgia State, he's my computational guy, and now I'm in DCN, so I think Samuel's kind of jealous because I'm going to be using CCAS for my computational, and also Robert that helped me with a lot of optical properties, and Frieder for he's on my last paper for helping me with some like for the physical property also. And also we'd like to thank all of our people that fund us. So the Photocage product was funded by NSF, and ACS PRF is funding the fluorescent with the boron, and also we have some funding from Howard Hughes Medical Institution, and also Aditya Below Carbon. And also like to give a big thanks to Kennesaw State University, of course, for giving me this beautiful lab and also a wonderful office to conduct all this research. Again, thank you for listening, and let me know if you have any questions.